I only use 5 right now. Did you know? I didn't know what else. Big problem. Yes. Well, I would.
Okay, guys.
But you need a value to input. You don't need to be good, everyone's good. Isn't that zero? No. You just.
Okay, so today we are very busy today, so if you want to talk, and you can talk after the class. The first thing I want to ask is that I sent out a survey, right? Survey link. I will receive the survey link. Okay, we have received the survey link. Can you do me the favor to fill out the survey? So I want to hear the feedback from you. So my goal is that I do not want to compromise the rigor of the academic work. However, I want to enrich your learning term. I want my students to be happy and at the same time learn all these things that they are supposed to learn. Is it okay?
Yes.
Sure. So do me a favor to fill this out by this Wednesday. Also for I have another link for the manufacturing processes. I want my students, what the feedback my students have for me. And then we can just adjust. Just I want to make sure my students they are happy and at the same time learn all these academic skills. So this is my goal. You will not be, I will not punish you, right? Or you can write whatever you want to say, but constructive things, and then I will consider your feedback. Right, so this is one thing. Second thing is today I'm going to finish this example, and we have I'm going to talk about our advocacy modeling for the shaft very briefly, and then I'm going to go to another example about the flywheel, the designing. So we are very eager today. So this is what I have. So I just use the photo that I took last Friday. So here is for this is PA, okay? For this is PA. I have the equation. I have the equations. And for this is if the point is located to the left of PA, and I have one equation. If the point is located to the right of PA, I have another equation. So this equation usually generates the same value for the point A, right? So as this is where you apply the load for the PA for the force, not just the PA, any this concentrated force. So this here is I introduced this delta deflection as a delta AA for here, okay? So here, and delta AA means that so this is a deflection at location A. Okay, at location A, first A is the location, and second the subscript is where you apply the load. So delta AA means that my deflection at point A because of the load that is applied at this point A. And then for here is a B, this AA, okay, so B equals this is A, and this B equals the sum of x2 plus x3. So we can get delta AA. So, and then delta BA, and delta BA means that this deflection at point B, deflection at point B, and because of the load that is applied at point A. Understand? So that means I have this load, but now what I'm interested in is point B. And point B, then I need to use the second equation. So I use this equation. So this A is this, and B, this is B, x1 plus x2 is B. So I have delta BA that equals and this value. So this is where we arrived last time. Questions regarding this one? So this is, you can see, because of the applied force for the A, I can get delta AA and delta BA. And then because, so this is the structure, I have two concentrated force. And similarly, I just use the second so here is a point A. So here is a point B. Now I apply the force of PB. Now here is the supported. And here is the supported. Now, if this case, I have this force, then I can use this the same equation and to calculate. This is the deflection at point A and deflection at point B because of PB. So here for this case, okay, for this case, how we define the A value, the lowercase a. So this is our A, and so this is our B. And for this case, an A equals x1 plus x2. So this is x1, and so this is x2. And B equals x3. And why we need to have A and B? Because that equation, they are written in terms of A and B. For this case, the delta at point A because of B equals, I use my first equation that is applicable for the points to the left of the applied force and put here. So delta AB means that the deflection at the point A because of the load at the point B. And this equals P B multiplied by X, and then I have 6 L. L is the total length, EI. E is the Young's modulus, A is every moment of inertia. And so I have X L squared minus X squared minus B squared. So I have A equals this and B equals this. And you can just plug in, right? X1 equals, so this is X equals X1. This X equals X1 because this is point, this is X1. And you just plug in and you can get negative 0.03848 inch. So when you calculate this value in your homework, and don't just write 0.03, right? I want these significant digits. Questions regarding this one? No question? No question, and then we take a look at delta BB. And delta BB is the deflection of point B when you apply the load at point B. So this guy, so this is a demarcation line here, okay? So you can use either the equation for the left points or the equation for the right points, right? So I'm a lazy guy because I know B is okay. These two equations are both okay, so I just still use the same equation. I have P and BX and 6LEI and L square minus X square minus B square. Now this time, so this X is the distance between this here to the B. And so this time, this X equals X1 plus X2. Now this time, and I can have this value. Questions so far? No questions? And then we use, this is the principle of superposition. And the principle of superposition says that if we have two sets of these loading conditions, and for each set of these loading conditions, and we can get one set of answers. Then, when you apply these two sets of loading conditions together simultaneously, then the results will be the sum of the results from each of these sets of loading conditions. So this is called the principle of, this is the superposition, right? You understand, guys? So then we can have this is delta A, the total deflection at point A if you apply both PA and both PB. And delta A will be equal to delta AA plus delta AB. So this gives us negative 0.07922 inch. And similarly, delta B is a total B and total deflection and due to PA and PB. If I apply these two loads together simultaneously, I can have delta A and delta B. And delta B equals delta B because of A, because of load A, and plus delta B and because of point B, because of load B. And then I can have negative 0.062 inch. Okay with this step? And then we use a relay method, relay equation. And using relay equation, So relay is equation. So this is WCR for the whole system. The omega CR, I'm not going to say W. Omega CR equals, and this is G is the gravitational acceleration, multiplied by PA delta A and plus and PB and delta B. And then we have PA multiplied by delta A squared and plus PB multiplied by delta T squared. So this is inch. This is inch. The T is acceleration. And be very, very careful about the G, right? The G, we know that, and T equals 9.83 meter per second squared. You guys agree? If you have different value, let me know. This is what I have. So however, I'm using inch now. I need to unify the units. And so T equals, this equals 32.174 feet per second squared. Now, because I'm using inch, so this one I need to change to 386 inch per second squared. If you are using inch, you are supposed to use this value. Is it okay? So this one, and then I plug in, so this is PA, is a PA pound, and if I use the US customers, this is the units. So this I can have, so this value and will be WCR equals 74.14 radian per second. So this can be changed to the RPS 11.8 revolution per second, and then change it to 708 RPM revolution per minute. So we are mechanical engineers and we need to pay attention to the units, right? You can see the same thing if we use different units and this is the values are totally different. Questions? So one thing I want to mention is that when you use Rayleigh method, Rayleigh equation, so this is the deflection value and they are the total deflection values for each of these points. Understand? We're using delta A here. And when we use another method, the things are different, and we just use delta AA and delta BB. So this is the first one, and we use Rayleigh method. And the Berkeley method. Berkeley method. So Berkeley method, they have another equation. It says 1 over WCR, the whole system. Omega, I'll say omega, okay, and not say W. So 1 over, because we usually use omega as angular velocity. So W on CR because of load A square and plus WCR B square. So this is called the Berkeley method. So WCRA and can be calculated using this one. So G is accelerational, gravitational acceleration. So now this divided by delta A. Delta A. So that means this deflection is a deflection at point A because of load A only. So this is delta A. So this gives us, and you can just substitute, and we use 368 divided by delta AA, and here is my delta AA. Delta AA is 0. So negative. I'm sorry, this should we don't have this sign here, okay? Or it's 0.4 0.74. So you just get rid of the minus sign. It's a deflection magnitude. So this gives us 97.34 radian per second. And so you can change it to 15.49 RPS. RPS is revolution per second, and so this equals 929.5 RPM. So this is RPM. So similarly, and for the WCRB, that's because of the load B. And so this is WCRB equals CG and divided by delta BB. So this one, and you can just plug it. And I'm going to here we use 3686, and BB is this one. As I said, and only take care of the magnitude, and then the sign can be dropped. And point 03697, and so this one gives you 11.22 RPS. But usually you get the radian per second first, but I just ignore that one. So you can have something radian per second, and then I change it to 11.22 RPS, and then so this one is 673 on RPM. I'm sorry. I'm sorry. So let me finish this one. So here, so we have 102.2 billion per second. So this equals 16.27 RPS and equals 97.6 RPM. So I have this one and I have this one. And then using this equation, I can get my WCR squared. And WCR squared, WCR equals numerator WCR comma A multiplied by WCR comma B and then square root and WCR comma A squared and plus WCR comma B squared. So this gives us 11.22 RPS and equals 6073 RPM. You can see when we compare these darkly results and the really results, and you can see they are different, right? The darkly results, darkly method usually underestimate the value, and really method are usually overestimate the value. So we know this WCR is below in this range, on 673 and 708 RPM. So this is your critical value. And so as a result, when you apply any cyclic loading, make sure the frequency of loading stay away from this interval. Questions? Now you can see we can have delta AA, delta BA, and delta AB and delta BB, and how they are different, you should know that. And also, when you calculate the Rayleigh equation, and you use the T, right? Both in Rayleigh equation and the doubling method, and the T value. And T value, which value you should use, it is dependent upon on what values you are using for other variables. The bottom line is that you must be consistent when you use these values, because you need to make sure the units, they are consistent. Questions? A similar problem will appear in our the upcoming exam. Questions so far? No question? So no question. Have you got a chance to look at the charts I asked you to model? Not yet? When are you going to take a look? This Friday morning? The earlier the better. Right? I will finish just sending out, and you can just take care of other issues, take care of other systems. Don't wait until the last minute. In the short modeling, and I ask you guys, let me jump forward to the. as you can see, it will be till March 1st, morning. I'm sorry, evening, I'm sorry. Okay, if you give me morning, it's also fine. So these two problems, this Wednesday, I'm going to talk about these two problems first. This problem, because it is closely related to this example, I want to talk it now, right? And so here, so this is short, and you can use the tutorial video and to do this modeling. And after you finish it, and you finish the modeling, which is very, very good. And what I wanted to tell you is that, and so here, so this is the last one. So just you can see, okay, let's see. Our first one, neglect the mass of the shaft. Actually, this example, we did not take care of the mass of the shaft, right? So we only take care of the contribution and from these two concentrated forces. Do you guys agree? So this we simplify the problem. But now, here this example, first one, neglect the mass of shaft. It is very, very similar to this one. And I ask you guys to use abacus to put these two loads and then get these two deflections. And to then use Rayleigh method and Bernoulli method to calculate the critical speed. So you need to do the convergence test. So for this is Rayleigh equation. As I said, for Rayleigh equation, delta A and delta B, and they are the total deflections of these 2 points because of these 2 loads, right? And then you can, when you use abacus, and you can put both of these 2 loads simultaneously, and then you get delta A and delta B, and then put these 2 values here, and to get the WCR using the Rayleigh method. And however, and for this is the Bernoulli method, as I said, this is delta AA, and so this is delta BB. So to get delta AA, and you only need to apply the load A, okay? Apply the load A only, and then get this gas deflection. That is your delta AA. And then do the same thing, remove the load A, and then only apply the load B, and then get the load deflection at the point B. So this is your delta BB. Be very, very careful. So this is the first part. On the second part, and I ask you to consider the mass of the shaft. So this density is using this one. And use what we have learned in CAE model analysis, and to compute the first natural frequency of the shaft without load. Without load means I just treat this shaft as a third contribution. Right? So this is this one. And then we use Bernoulli method, use the Bernoulli method. So this is the Bernoulli method. And then we plus another one, okay? Then we plus another item that is called 1 WCR comma shaft. And right now? For the third part, and I ask you to use Bernoulli method and to take care of both of these 2 loads and the shaft. And how to do that, guys? And you are supposed to add another item. You are supposed to add here, okay? Another item. So this is a W and CR comma shaft square. How to get this one? And you use abacus, and you have, I suppose you have already got, and this guy's. And make sure, so this WCRA, WCRB, along with WCR shaft, and you are using the same units. Questions? Comments? Remarks? Yes? Do you like abacus? Honestly, no. Somebody is shaking his hand. Why do you love it? Okay, it can solve. This is a good tool. It can solve a lot of problems for you, technical problem. The powerful tool. No question. Then I'm going to talk about continuing our talk. Now this time we are going to talk about the flywheel. So this is what we have talked about, the problem and the Gillick method, the Berkeley method. And so this is an example we covered already. And then we talk about this is the keys and the pins. Because you have a shaft, if you have a shaft, you want to mount different various elements on it. How to do that? And to transfer on the top. And there are a lot of keys and pins. So this is a shaft. So this is another shaft. You want to put them together. You want to put them together. How can you put them together? And you need to have a key. Okay, so this key, if this inner shaft is transmitting torque, so because the key is a torque can be transferred to this is outer shaft. Without the key, that might be an issue. So these are different keys. The key, you can buy this key from the Lowe's or from the hardware stores. Lowe's we have. Lowe's have. I bought these kind of things from there. Or you can just Google search and to get much cheaper ones. So here is a dimensions of shaft with a keyway each shaft and half. So this is a keyway. We have this called as a keyway. Keyway means the place where we put the shaft. And so B is a square parallel key and square parallel key. And square means a square with respect to the axis. And so this is a C. This is the flat parallel key, and the flat parallel a little bit is a flat. This is a D is a taped. E is a taped. Taped key. So E is a taped key with this give head, and this give head is used to secure it. So here it is a give head. And last one is a round key. So this is the round key. Last one is the round key G here. So this is the wood rod the key. Wood rod key, which is half of the cylinder like. Here's the pin. The pin is going through. So these are two of the shaft. This is the pin here, which is often the groove. This is the groove here. And so this is the roll pin. Elastic deformation of the pin in a smaller hole leads to the friction forces that keep the pin in the place. So here, if you just take a look at, if you use imaginary plane cardio here, and then you see this view at this point, at this thing here. So these are different keys. The plane parallel key, parallel key this is commonly used one. So here as a mechanical engineer, when we design something, and you do not need to design the keys, right? So your task is based on your needs and select appropriate key. How to get it? You need to find some vendors and then ask them for this is categories for different keys. Then based on needs, and you just select a key. So we use this is the components that have been built and made in mass production. This is a diagram. Standard, we will say these are standard keys. So using standard keys can save us a lot of time and money. So shaft diameter, based on the shaft diameter, the key width in distance from the key seat to opposite side of shaft, you can see different based on different the shaft. So taper the key,
and tapered key is a little bit different from the previous key, and they also shaft diameter based on the shaft diameter, and then you can have. So this is a square type, flat type, and so these are available lengths, and you can have. So this is a wood roof key. A wood roof key is kind of interesting, and also the key number, and so the shaft size, normal key size, height of key, the shear area, and all these things they are given. You can just need to get the category from the manufacturer. So set screws, in addition to the keys that we can select to transmit the torque from one shaft and to the other movements mounted on the shaft, and we have set screws. And set screws resist this axial and rotational motion. Set screws, I'm going to show this. Just to put it in. So they apply a compressive force to create friction. The tip of the set screw may also provide a slight penetration, and various tapes are available. You can see the tapes, various tapes, they are available. So set screws, so here's a different size number. So the seating torque, they can just carry, and holding power, and they can provide. So this is a resistance to axial motion of collar or half relative to the shaft is called the holding power. And typical value is a typical value. And typical factors of safety are 1.5 to 2.5 for static and 4 to 8 for dynamic loads. So length should be about half the shaft diameter. If it's too short, it will not too much sense. It will not make too much sense. Then we talk about the flywheel. You guys know flywheel, do you know? The flywheel, the wheel that is playing, right? Flywheel. So flywheel with driving torque. So we suppose we have a driving torque Tm, and so this is the TL, and load torque TL. The functions. So flywheels reduce amplitude of the speed fluctuation. So if you have a flywheel on the shaft, and you can reduce the fluctuation, so make it a stabilizer, acts as a stabilizer, and can reduce maximum torque required. Maximum torque required, and it stores or release energy when needed during cycle. So this is, we can treat this one as a very, very old type, the battery, right? So if we have much energy, the energy is stored here, and then if we need energy, we can just ask the flywheel to release the energy. But that's a dynamic energy. It is very, very old, the battery type. Questions? I'm going to ask you guys to tell me this. I'm going to the flywheel. What are the functions for flywheel? So coefficient of fluctuation. So coefficient of fluctuation, because the wheel usually, so this is the shaft is usually rotating. It's not as a normal. It's not as a stable. This is a rotational speed, and so we will have fluctuation. So here is a coefficient of fluctuation for various type of equipment. So here, what is a coefficient of fluctuation? So it is the maximum velocity, angular velocity, minus the minimum one divided by the average, the angular velocity. So this is how we define the coefficient of fluctuation. And for different types of equipment, and we have different coefficient of fluctuation. I need to tell you guys, so all these values, they are not accurate values. And they are just give us an average empirical value. Right? So as a mechanical engineer, if you are asked to handle these kind of things, and you are supposed to get your accurate coefficient of fluctuation. How to do that? Through experiments. Right? Questions regarding this slide? So this is CF, and we are going to use CF and for our calculation. So how to design a flywheel? And so we have, so these are detailed procedures. And first one, we need to plot the load torque on TL versus theta for 1 cycle. So this flywheel, this cycle is rotating 1 cycle. 1 cycle means on 360 degree, 2 pi, right? So this is called 1 cycle. And first one, we plot the load torque TL versus theta. So within this is 360 degree, and I want to know how this TL changes and with this is theta. And then determine the TL common average. This is average value of T over 1 cycle. And then find the location theta theta omega max and theta omega mean. And so these two values shows where it is, the theta value, where it is when the angular velocity is highest one. This one is where it is when the angular velocity is lowest one. And then we determine the kinetic energy by integrating the torque curve. And then determine this omega average, and then determine IM. Right? What is IM? IM is calculated using this equation. KE is the kinetic energy divided by CF omega average square. So this is how we calculate. This is IM. And after we get this IM, and we know the density of the material, and the material you will be given. What the material? So this flywheel will be made of. You know the material, you know the density, and also this is the size, and depending upon the size, you can get this is H, and then you can calculate this is this IM is the mass moment of inertia. So write down as IM is the mass moment of inertia. IM is it equals KE and divided by CF. CF is a frictional coefficient of fluctuation multiplied by W of the omega AV average and square. So IM is called mass moment of inertia. It is mass moment of inertia. It is different from area moment of inertia. Okay, area moment of inertia is a geometric value, but this guy is associated with the mass density also. So for this is a disk, and for the disk, IM is calculated using this one. MA and D squared divided by 8. So what is MA? MA is a mass. It's a mass of the disk. And so the mass of the disk, this is, let me write down. MA equals pi e power 4, e power 2 divided by 4, then e pi e square divided by 4 is what? Is the area, right? Area then multiplied by thickness. And multiplied by the thickness, then multiplied by rho. So MA is a mass of the disk. And usually here we use this is the round. We use the circular disk. So one more time, D is the size that we are going to solve for. And so this is pH is the thickness of your flywheel, and rho is the density. So then we will have pi d square over 4 multiplied by th and multiplied by rho, and then and d square and divided by 8. So this is the density. Rho is the density. So this is thickness of the plate of the disc. I'm going to stop here now. So this Wednesday, I'm going to finish our example of flywheel design, and also I'll talk about the formula problems. I think we have one implemented.
Yeah.